So we have seen in our last class the Einstein's theory of lattice heat capacity. Today we will discuss about Debye's theory of lattice heat capacity. So in the Einstein's theory, he assumed that the atoms of the crystal vibrate totally independent of each other, that each atom vibrates independently, and the vibrational motion of the crystal as a whole was considered to be the same as the vibrational motion of a single atom, and therefore all the atomic vibrations of the crystal were assigned a common frequency omega 0, which is the natural frequency of vibration of a single atom. This assumption is oversimplified since the atoms are bound together in a crystal and form a system of coupled harmonic oscillators which cannot vibrate independently. So in the Einstein model, he assumed that each atom vibrates independently, so that the system as a whole considered to be a single atom having a single natural frequency omega 0. So this was an oversimplified case, and so still there was a discrepancy with the classical experimental observation of the heat capacity. So this oversimplified case was taken into consideration by Debye in 1912, and he put forward this model of lattice heat capacity by considering this point also. In his model, the vibrational motion of the crystal as a whole was considered to be equivalent to the vibrational motion of a system of coupled harmonic oscillators, which can propagate a range of frequencies rather than a single frequency. So in Debye model, he considered instead of a single frequency oscillator, he considered the system as a coupled harmonic oscillators, so that a number of frequencies are possible instead of a single frequency of vibration. So Debye proposed that crystals can propagate elastic waves of wavelength ranging from low frequencies, that is of the order of sound waves, to high frequencies corresponding to infrared absorptions. So according to his model, a range of frequencies can be propagated ranging from low frequencies to high frequency. This means that a crystal can have a number of modes of vibration. The number of vibrational modes per unit frequency range is called density of modes, which is represented by Z of nu. Nu is in the sense of frequency. So the vibrational modes per frequency range is called density of modes, which is represented by Z, which is a function of frequency. We now determine the density of vibrational modes of crystal, treating it as a continuous medium. So now we'll find out the density of modes, that is the density of vibrational modes. So for this, consider a one-dimensional continuous string of length L. Here I have shown this is a string of length L. Let it vibrate in a longitudinal mode with both ends fixed. Suppose these ends are fixed and it's execute vibrations in longitudinal mode. Let X be the position of a line element. So this is the position X of line element, and U of xt its displacement from the mean position at any time t. Therefore the amount of strain E is given by E is equal to du by dx. Strain is change in dimension to the original change in dimension to original dimension. So U represents the displacement, so which is a change, which represents a change, and X is its original line element. So the strain can be represented as du by dx. So this represents strain, which is represented by the letter E. If this strain is produced by a force capital F and Y is the Young's modulus of the strain, then for a unit cross section we can write F by E is equal to Y. Since Young's modulus can be defined as stress by strain, stress is represented by this force and this is strain, so this Young's modulus Y is F by E. Now consider an element of length delta x, elemental length delta x in the string. If the strain at one of its end is E of x, then its value at the other end is represented as E of x plus dou E by dou x into delta x. Since we are considering an elemental length delta x and E of x is the strain at one end, so delta x is the elemental variation of the length, so dou E by dou x is the elemental variation of the strain. So this, the propagation of strain through this length delta x is represented by is dou E by dou x into delta x. So this will be the strain at the other end. So this will represents the propagation of the strain along the elemental length delta x. So we can write this expression as dou square u by dou x square instead of dou E by dou x. Since E is equal to du by dx, dou E by dou x can be represented as dou square u by dou x square. So this expression will become like this, and the force at the two ends of the string is E of x into y. E of x into y and E of x plus dou square u by dou x square into delta x into y. So the force expression is we are getting this expression from this F is equal to E into y. This is strain, this is Young's modulus. So from this, the both ends, the force acting at both ends can be represented as F is equal to E of x into y and F into E of x plus dou square u by dou x square delta x into y. So the net force acting on this element is the difference between these two forces. So if we find out the difference between these two forces, this is at one end, this is the force at other end, if the difference of this force will be the net force, which is dou square u by dou x square into delta x into y. The force on the line element delta x can also be written as, so this is the net force, and the force can also be written according to Newton's law as mass into acceleration. Okay, mass into acceleration, and rho delta x will represents the mass, where rho is the density, and dou square u by dou t square represents the acceleration since u is the displacement. So this again represents the net force. So these two forces can be equated since this represents the same quantity. So if we are equating these two equations, we will get dou square u by dou x square as rho by y dou square u by dou t square. So this is 1 by vs square dou square u by dt square, where vs is square root of y by rho, which is the velocity of, so we will get dou square u by dou x square like this, and where vs is square root of y by rho is the velocity of propagation of the wave along the string. It is independent of frequency. So this equation is a well-known one-dimensional wave equation. Since the string is fixed at both ends, the solution of this equation should correspond to a standing wave. So we have already said in the beginning that the ends of this string is fixed. So since these ends are fixed, the solutions of this wave equation will be a standing wave. So this type of solution can be of the form u of xt is equal to a sine n pi by l x into cos 2 pi nu suffix n t. Nu is a frequency. Okay. This is a sine function, this is a cosine function. A combination of these two will represent a standing wave equation. So this will be the solution of this wave equation, where n is a positive integer which is greater than or equal to 1. And from this equation we can find out dou u by dou x, dou square u by dou x square, and dou u by dou t, and dou square u by dou t square, and substitute back into this wave equation. Here we have dou square u by dou t square and dou square u by dou x square, and we will find out these two, dou square u by dou x square and dou square u by dou t square, and put back into this wave equation. And after substituting, we will get an expression like this: n pi by l whole square into 1 by vs square into 2 pi nu n all square. Now we can put nu n as vs by n, that is the frequency is velocity by wavelength. So if we are substituting this nu n as vs by lambda n in this equation, we will end up with here I have shown the substitution. If you are substituting this, after solving, we will get lambda n square as 4l square n square, so that lambda n will become 2l by n. So we will get lambda n is equal to 2l by n, and also from this we will get, from this expression we will get nu n is equal to n vs by 12. And note that this is nu frequency, this is v, which is velocity. Okay, so we will get the expression for lambda n and nu n. So from this expression, the different frequency, this is the expression for frequency, the different frequencies can be obtained as v1, which is equal to vs by 12, and v2, which is vs by l, and v3 is equal to v3 vs by 12, etc. So this shows that the frequency of the string can have discrete values only and is an integral multiple of vs by 12. So what we have obtained is, we have obtained discrete frequencies okay, and which is a multiple of vs by 12. It implies that the frequency spectrum of a continuous string is discrete and contain an infinite number of parallel lines equidistant from each other. So since these frequencies are integral multiple of vs by 12, it is clear that the frequency spectrum is discrete and which will have parallel lines which are equidistant from each other, just as shown in this figure. Okay. Now we know we know the expression of nu n. From this we can find out what is n, which is equal to 2l by vs into nu n. From this dn can be represented as 2l by vs into d nu. This gives the number of possible modes of vibrations in the frequency interval d nu. So this is the number of possible modes of vibration. Considering now the three-dimensional case, the wave equation can be written as, in the three-dimensional case, the wave equation become instead of this dou square by u by dou x square terms only, there are two more terms in y and z, and the right side become 1 by v square dou square u by dou t square. The three-dimensional continuous medium can be taken as a cube of side L whose faces are fixed. The standing wave solution for this equation can be, for this wave equation in three dimension, can be written as u of xyz into xyz t is equal to a sine n x pi x by L n y pi y by L n z. That is, there are terms in x, y and z and the cos term 2 pi nu t. This is the solution for three-dimensional case where nx, ny, nz are positive integers greater than or equal to 1, and substitute this solution. That is, we are finding out, if you are finding out this dou square u by dou x square and dou square u by dou y square and dou square u by dou z square as in the previous case, and substitute back into this equation, we will end up with this equation pi square by L square into nx square plus ny square plus nz square is equal to 4 pi square nu square vz square vs square. So that this will become 4 L square nu square by d square, because there is a pi square here, pi square which will be cancelling out, and L square come here. This equation gives the possible modes of vibrations. The integers nx, ny and nz determine the possible frequencies or wavelengths. In order to determine the number of possible modes of vibration, which is said of nu d nu present in the frequency range nu and nu plus d nu, we consider a network of points in the space defined by the positive integral coordinates nx, ny and nz. So what we are doing is, we have to find out the density modes of vibration, or the number of modes of vibrations in the frequency range nu and nu plus d nu, which is represented by set of nu d nu. We are finding out an integral space defined by the values coordinates nx, ny and nz. So the radius of this vector at any point from the origin is given by r square, which is nx square plus ny square plus nz square, because the coordinate specifying this field is nx, ny and z. So this will represent the radius. So this is nothing but 4L square nu square by Vs square. So we can write this here. This is the equation of a sphere of volume V prime, capital V, 4 by 3 pi r cubed. So this will represent a volume of 4 by 3 pi capital R cubed. If we differentiate this equation, we will get dV prime as 4 pi r square dr. So the total number of modes present in the frequency range nu and nu plus d nu should be the same as number of points lying in the volume interval nu and nu plus d nu, or in the range r and r plus dr of the radius vector. So since each point occupies on an average a unit volume in the space of integers, the number of points present in the volume dV prime of the spherical shell is numerically equal to the volume of the shell. Okay, so it's quite clear that each point occupies on an average unit volume, and so the number of points present in the volume dV prime of the spherical shell is numerically equal to the volume of this shell. So which is represented as dn, which is 4 pi r square dr. But since a mode of vibration is always determined by the positive values of nx, ny and nz only, we must consider the number of points lying in the octant defined by these positive integers only. Because the coordinates are nx, ny and nz, so we have to consider the points which is defined by the octant of these coordinates. Thus the number of possible modes of vibration can be written as z d nu, which is 1 by 8 of 4 pi r square dr. This is the volume specified by the, or the field specified by the octant. So we are substituting instead of r square this expression and dr from this expression. So we will get these two terms here. After solving this, we will end up with this equation, and which is, and for L cube we are written volume. L cube is volume. So 4 pi v by vs cube into nu square d nu. This is the possible modes of vibration in the frequency range nu and nu plus d nu. For a perfect continuum, the possible frequencies vary between 0 and infinity, and the number of possible vibrational modes increases with square of the frequency as obtained in the equation. So it is clear that it is varying as square of the frequency. So for a perfect continuum, possible frequencies vary between 0 and infinity, and the number of possible vibrational modes increases with the square of the frequency. So it is shown in the graph here. It is here it is frequency, and this is the modes of density of vibration. This type of situation arises in case of electromagnetic waves traveling in a box. So in general, the elastic waves propagating in a solid are of two types, transverse and longitudinal. The velocity of propagation Vt, the velocity of propagation, this is Vt, T for transverse waves, is generally different from the velocity of propagation Vl for longitudinal. L stands for longitudinal. Also, for each frequency or direction of propagation, the transverse wave have two vibrational modes perpendicular to the direction of propagation, whereas the longitudinal waves have only one mode which lies along the direction of propagation. So the velocities are different for V transverse and VL mode. So for each frequency or direction of propagation, the transverse waves have two vibrational modes perpendicular to the direction of propagation, whereas the longitudinal mode only one mode lies along the direction of propagation. For such a case, the total number of vibrational modes is represented as 4 pi v into 2 by v t cube. Since we have said two modes of vibrations for transverse, so 2 by v t cube. So here in the original expression this was v cube, 1 by v cube. So this 1 by v cube now changed to two terms, one corresponding to the transverse mode and another one corresponding to the longitudinal mode. And this transverse mode has two modes of propagation. So here at 2 comes here, 2 by vt cube plus, and one mode correspond to longitudinal is 1 by vl cube into v square d nu. So this will be the density of modes corresponding to the propagation. Okay. Now we will discuss the Debye model or Debye approximation to this heat capacity model. If the interatomic distance is small as compared to the wavelength of the elastic waves, the crystal can be regarded as a continuum from the point of view of the wave. This point is very important in this model. So what he tells that if the interatomic distance is as small compared to the wavelength of the elastic waves, the crystal can be treated as a continuum from the point of view of the wave. Based on this idea, Debye assumed that the continuum model is applicable to all possible vibrational modes of the crystal. Further, the fact that the crystal consists of a finite number of atoms, which is represented by n, finite number of atoms is taken into account by limiting the total number of vibrational modes to 3n. This puts an upper limit to the frequency of the elastic wave, which can propagate through the crystal. So this assumption is putting a limitation to the upper modes for frequency, which is 3n. Okay. That is in the assumption that the crystal having n number of finite atoms, we are taking into consideration these atoms, and that's why the possible modes of vibration is limiting up to a value of 3n. Okay, the highest frequency propagating through a crystal is called the Debye frequency, which is represented by nu d. It is common to transverse the longitudinal modes of vibrations. The highest frequency propagating through the crystal can be called Debye frequency, which is nu d, and it is common to transverse and longitudinal modes. Hence, the frequency spectrum of a continuous medium is cut off at the Debye frequency. So the figure can be shown here. The highest frequency is cut to this highest frequency, which is Debye frequency. For the total number of vibrational modes with the frequencies ranging from 0 to nu d, we can write integral 0 to nu d z of nu d nu is equal to 3, because this is the upper limit, and this represents this total number of, or the frequency, total number of frequency modes of vibration. Now, if we are substituting for set of nu from our previous equation, if we are substituting for set of nu, so this equation will become like this, and this integration is with respect to nu, so we are integrating this term only. This will nu cube by 3, and putting the limit values, we will get nu d cube by 3, and the remaining terms are here, which is equal to 3n. From this we will get nu d cube, which is the upper value of frequency, as 9n by 4 pi v into 2 by vt cube plus 1 by vl cube whole to the power minus 1. This equation can be used to determine Vd. Taking velocity of sound of the order of 10 to the power 3 meter per second, and n by v, this value n by v approximately 10 to the power 28 per meter cube, we get the upper frequency limit as 10 to the power 13 per second. This corresponds to a wavelength of 1 angstrom, which is the same order as interatomic distance. So by substituting these approximate values, we will get a wavelength of 1 angstrom, which is approximately equal to the interatomic distance, which is this violates the basic assumption of Debye, which was the first point, or first assumption about the Debye will be said in the we talked about in the beginning, and hence puts a question mark on the validity of the quantum theory, particularly in the high frequency region. Further, the velocities Vt and Vl have been assumed to be independent of wavelength, which may not be always true. And this independency also, these velocities are independent of wavelength, which also may not be true. The vibrational energy of a crystal is determined by using the Planck's theory. The average energy of an oscillator having frequency nu at a temperature T is given by the expression h nu by e to the power h nu by kt minus 1. We can associate a harmonic oscillator of the same frequency with each vibrational mode. Thus the vibrational energy of the crystal can be given by E is equal to integral 0 to mu d energy into density of modes. So this represents the energy, and this represents this represents the average energy, and this represents the total number of modes of vibration, and the total of this will give you the total energy. And we are putting the expression for Z nu here, and expression for energy using this Planck theory. And after integrating and substituting the limits, so we can integrate this by taking the constants outside. The integration is with respect to nu, so we can keep the terms having nu inside the integral. We will get the expression like this using equation 82. So for Vd cube, so we have got one expression here. We can use this expression here in this. So this form will reduce to this form, and inside this integral, this will these terms will be exactly like this. This we have rearranged using the previous equation, and we are putting here h nu by kt as x. So h nu d by kt as xm, which is x maximum in the sense, and nu as x kt by h from this, or d nu is kt by h into dx. Therefore this expression E becomes 9nh by Vd cube and kt by h. For putting nu this expression, and we are putting this h nu by kt as x. So after substituting, this equation will become like this, and this will reduce in this form. Okay, we are changing the limit accordingly, so it will change from 0 to xm. As in the Einstein's theory, we introduce here a characteristic temperature theta d called Debye temperature, which is h nu d by k. So xm can be defined as theta d by kt. Sorry, theta d by t. So this expression, energy expression, become, after substituting this, will become 9 n kt t by theta d whole cube integral. This limit then may change to theta d by t into x cube dx by raised to x minus 1. The specific heat is then given by dou E by dt, or that is differentiating this with respect to t at constant volume. And so this equation after differentiating will become like this, and which will be 3r theta d by t into fd for n into, for n is equal to Na, which is the Avogadro's, that is for 1 molar substance. So the function fd is called the Debye function, and is nothing but fd, which is equal to 3 into t by theta d whole to the power integral 0 to theta d by t raised to x raised to 4 by. That is, what we are doing is, from this expression we are defining a function fd, and this is substituted here fd. So this is the heat capacity for 1 molar substance. Okay, so we will discuss the different cases of temperature effect. So for high temperature case, for T very much greater than theta d, for T very much greater than theta d, what happens? Then X is small compared with the unity for the complete range of integration. So this is this we are explaining just as we explained the Einstein model. What we are doing is, we are just substituting the conditions theta T very much greater than theta d and T very much less than theta d for low temperature case, and we are finding the integration values. So X is small compared with the unity for the complete range of integration. Therefore we can write e raised to x minus 1 approximately x, that is the e raised to, when we are expanding e raised to x, this will become 1 plus x, we keeping the first order term only, and minus 1 will cancel out 1 plus e raised to x plus etc minus 1. So this 1 and 1 cancel out, we will remain with, we will remain with x only. Then this equation, the equation for energy, this expression will become 9 nkt t by theta d all cube by into integral e raised to 0 to theta d by t x square dx. So after substituting these values, after integration and substituting this limit, we will end up with a 3 nkt, and the heat capacity after differentiating with respect to T will give you 3 nk, which is 3R for N is equal to Na. Na is Avogadro number for 1 molar substance. Thus at high temperature, the Debye theory also obeys the Dulong-Petit law, as in classical theory and Einstein theory. So at high temperature, both the Einstein theory and Debye theory matches with the classical theory, and which obeys the Dulong-Petit law. So that's what's clear from this. And at low temperature, what happens? At T very much less than theta d, x maximum, which is theta d by t, which is tending to infinity, since t is very much less than theta d. So that our equation of energy, 87 is the equation of energy, becomes like this. If we are substituting this expression, if we are substituting this expression in this theta d by t, this condition into this energy expression, this will reduce into this form. So now this expression, this integral, this is a definite integral which having a value pi to the power 4 by 15, pi to the power 4 by 15, and if we substitute back into this equation, we will end up with an energy expression like this. Okay, now this shows that the vibrational energy is proportional to T to the power 4. Here there is a T to the power 4 term, so vibrational energy is dependent on T to the power 4, which is analogous to the Stefan's law of black body radiation, which is sigma T to the power 4. Okay, thus it follows that both phonons and photons obey the same statistics, except with the difference that photon obey T to the power 4 law at all temperature, whereas phonon do so only at low temperatures. Okay, so if we differentiate this energy expression with respect to T at constant volume, we will get the heat capacity, which is this from the previous equation. And for N is equal to Na, this will become 12 by 5 pi to the power 4 R into T by theta d whole cube. Thus at very low temperature, the specific heat is proportional to T cube. So you can see a T cube term here, which shows that Cv, the heat capacity, is proportional to T cube. So this follows a T cube law. This is called the d by T cube law and holds for T very much less than theta d by 10. So by this theory, there is an excellent matching of the experimentally determined values of the specific heats at load at various temperatures with those calculated theoretically using the Debye's model. In the classical theory, the theory was not matching at low temperature, because it was not at all depending on temperature, but actually experimental values showing a dependence on temperature, which was falling to 0 when temperature goes very low. And according to Einstein's model, it was shown at least some dependency on temperature, but it was not according to T cube law. but by the Debye theory, Debye model, it was shown an exact matching with the experimentally predicted values. Okay, so a graph is shown here for the a comparison of result of the specific heat obtained from the Einstein and Debye model is shown in second graph, this graph. Okay, this is a Debye model, this is for Einstein model. So this was exactly follow the this for Debye, this for Einstein, and this was exactly follow the experimentally predicted values. The Debye model yields somewhat higher values of specific heat as compared to Einstein model. This is because of the fact that the Debye model takes into account the low frequency modes which at low temperature have high vibrational energy and hence large specific heat. So this is quite clear. Now the Debye temperature theta d can be obtained from equation 82 and 86. 86 is this, 82 is this equation. Okay. Provided the velocities of the sound and transverse and longitudinal modes waves are known, because this expression have these terms. For isotropic medium, one can use the average velocity Vs and replace the factor this by 3 by Vs square. So in an isotropic medium, these two particular frequencies can be replaced with Vs. And so this term can be replaced by 3 by Vs square. Okay. Alternatively, theta d is chosen to be that value which produces the best fit between the experimental data and the expression that we got finally for this heat capacity. There is in general a good agreement between the theoretical and experimental results. So accurate measurements have indicated that the temperatures at which the T-cube law holds are quite low. According to this model, the law should hold for temperatures below 0.1 theta d, whereas it may be strictly valid for T less than theta d by 50. So the specific heat is, however, relatively insensitive to the variations in the density of modes. Okay, so this is about Debye model of heat capacity. So it's found quite matching with the experimental values we measured for heat capacity. So what are the limitations of this model? The limitations of this Debye model are: the Debye's continuum model is valid for long wavelengths only. That is, only low frequencies are active in the solid. So this is one limitation. And the total number of vibrational modes are assumed to be 3n. Thus, it is difficult to justify, as the solid is considered to be an elastic continuum which should possess infinite frequencies. And the third point is, the cutoff frequency is assumed to be the same for both longitudinal and transverse waves. This is again difficult to justify because different velocities of transverse and longitudinal waves should employ different values of cutoff frequencies for these waves. So same cutoff frequency for both longitudinal and transverse wave is again a drawback. According to this theory, theta d is independent for temperatures, whereas actually it is found to vary up to an extent of 10% or even more. And the theory does not take into account the actual crystalline nature of the solid. The theory cannot be applied to crystals comprising more than one type of atoms. So it is actually not taken into consideration the very crystal nature of the solids. So, and the last point is the theory completely ignores the interaction among the atoms and the contribution of electrons to the specific heat. So this electron contribution to heat capacity is completely ignored and not considered in this theory. So these are the limitations of this model. Though it have found good results with the experimentally observed value of heat capacity, this theory have this much of limitations or limitations. Okay. So this is about Debye model of heat capacity. Okay.